For our first question, we have a truck with a 1,000 kg load sitting on its flat deck, circle of radius 100 meters. It's on a flat horizontal road and it's going at a steady speed of 10 meters per second. The load isn't secured, but it's not sliding. So which one of the following statements is false? So with these type of questions, I like to just work through the options one by one. So first of all, we'll look at option A. So the magnitude of the acceleration of the load is 1 meter per second squared. So we have this is the path of the truck, and we know that the radius is equal to 100 meters. And so if this was the truck here, and there was no centripetal force, it would want to keep going in a straight line, but there's some centripetal force that's pulling it back towards the center. So in this case, this would be the friction from the tires of the truck, which is causing it to, so there's going to be a centripetal force, so FC, which is bringing it towards the midline. And of course, so if an object is moving in a circular motion, there's always going to be acceleration, because remember that velocity, so acceleration is the change of velocity over time, and velocity is a vector, which means that it has direction and a magnitude. Okay, so if the direction, so this truck here is going at a constant velocity, so the magnitude of the velocity vector isn't changing, but the direction is. So that means that there is a change in velocity because the direction is changing. So there's always going to be acceleration, a centripetal acceleration towards the center of the circle. Okay? So an object that is moving in a circular motion is always changing direction, therefore the velocity is always changing, which means that it has acceleration. So what we want to calculate is the centripetal acceleration of the load. So that's A for acceleration and subscript C, which means centripetal. And the equation for that is V squared over R. So our velocity is 10 meters per second. So 10 squared over our radius, which is 100. So 10 squared is 100. 100 over 100 is equal to 1 meter per second squared. So we can see that option A is true. Okay. So we want to look for the false option, so we'll move on. And now we're going to look at option B. The upward normal reaction force on the load is 10,000 newtons. So the normal force is the weight, is the force that pushes back up in response to the weight force. So the normal force is just mass times gravity. Okay, so we know that the mass of the load is 1,000 kg. So 1,000 times 10 gravity. That's going to be 10,000 newtons, right? So option B is true as well. Oh, just those people over there, I think. So just put your hand up if you need a handout. Okay. Cool. Yeah, just keep your hand up if you need a handout, and she'll hand it out to you. She'll come around. Okay, so we'll look at option C now. So the total vertical force on the load is 0. So in our blurb there, it's told us that we're on a flat horizontal road. That means that there's no vertical movement up or down. So that means that the vertical acceleration is 0. So option C is also true. So now we'll look at option D. The total horizontal force on the load is 0. So we just said that the load has acceleration, right? Can you have acceleration without a force? You can't. So that means that option D is false, because there has to be a horizontal force on the load in order to cause that centripetal acceleration, and we can calculate the magnitude of this horizontal force on the load, and that's just going to be Fc, so C for centripetal, is equal to mv squared over r. So the mass is 1,000 kilos multiplied by our velocity, which is 10 squared, which is 10, and then that squared, and then divided by our radius, which is 100. So if you did that, you'd get an answer of 1,000 newtons. Okay, so that's the centripetal force acting, and that's a horizontal force acting on the load, and so that means that D is false, but that also is the calculation for option E. So the magnitude of the frictional force on the load is approximately 1,000 newtons. So that's what we've just calculated. Okay? So it's the friction from the truck deck on the load that's causing that centripetal force. Okay, so number 2, a cannonball is fired from a cannon at an angle of 60 degrees above the horizontal. The speed of the cannonball as it leaves the end of the cannon is 23 meters per second. Assuming that air resistance is negligible, how high above the end of the cannon will the cannonball go? So we're looking for the maximum height of this cannonball. Okay? So because we're only interested in the vertical component of this ball's motion, right? So we're only interested in the height, which is the vertical component. What we can do is, we've been given the total velocity, or the speed of this cannonball. We can figure out what the vertical component of this cannonball is, of this cannonball's velocity. So to do that, we just turn this into a right angle triangle. Sorry, I'll just do that in a different color. So this is going to be our vertical component of our velocity of the cannonball. So we'll call this v subscript y, so for the y-axis. So this here would be our hypotenuse, because this is the long side. So we have a right angle triangle here. This side is going to be opposite our angle that we've been given. So this side is our opposite side. So we've got the opposite and the hypotenuse, so that's O and H. So if we use SOHCAHTOA, the one that has, so we have SOHCAHTOA, we have O and H, so we're going to use SO, and SO is the sine of theta is equal to the opposite over the hypotenuse. Okay? And so if we write that again, the sine of 60, so remember that for Physics 191, your calculator should be in degrees. All your angles are going to be in degrees. So sine of 60 is equal to our opposite. So our opposite side is going to be Vy. Vy over our hypotenuse, which is 23 meters per second, or just 23. So in order to get Vy on its own, you're just going to multiply both sides by 23. So 23 multiplied by sine of 60 is equal to Vy. So if you do that in your calculator, you'll get an answer of 19.92 meters per second, which is the vertical component of your velocity. So we know that's 19.92 meters per second. But that's not the end of it there. So we're about halfway there. Okay, so now we're just interested in the vertical component, right? So we can now call this our distance. And from now on, we'll just be thinking in terms of vertical. So our vertical distance is what we're looking for. So D equals question mark. And this, if you throw a ball straight up in the air, what's the acceleration going to be? Yep, so negative 10, right? Because it's going to be accelerating towards the ground. So our acceleration will be negative 10 meters per second squared. Our initial velocity, so our initial velocity when it was going up was 19.92 meters per second. That was the vertical component of our velocity. So initial velocity is equal to 19.92 meters per second. And our final velocity, so when it's right at the top of this apex here, it's going to have, for a split second, it's going to have a velocity of 0. So we know that our final velocity will be 0 meters per second. Okay, so now we have our variables. So we have D, A, Vi, and Vf. So if you had your cheat sheet or your equation sheet, you just look for the equation that has all 4 of these variables, and that's going to be this one here. So D is equal to Vf squared minus Vi squared divided by 2A. Okay, so that's your equation there. And you can have that rearranged for Vf, Vi, or A. So that's what I'd recommend doing. Okay, so now we're just going to substitute our numbers. So our final velocity was going to be 0, so 0 squared minus our initial velocity, which was 19.92 squared over 2 times our acceleration. So our acceleration is going to be negative 10. Okay. So I've just put this 0 squared in there, but because it's 0, you wouldn't have to actually put it in. I've just put it in there so you guys don't get confused. And if you do that in your calculator, you should get an answer of 19.84 meters, which is just 20 meters. Okay, so that was a bit more complicated. Okay, so number 3, a girl pushes a box of mass 20 kilograms across a level floor where the coefficient of friction is 0.5. Which one of the following statements is false? So Again, these types of questions, you just want to work through each of the options one by one. So we'll look at the option A. The normal reaction from the floor is about 200 newtons. So we're just talking about the box here. So the normal force is just equal to mg. So we know that the mass is 20 kilograms multiplied by gravity. So that's going to be 200 newtons. So option A is true. So we'll move on. Option B. If the box is accelerating, the force exerted by the girl on the box must be greater than the force which the box exerts on the girl. So is B true or false? So this one's going to trip a lot of people up, but it's false, okay? Because the force exerted by the girl on the box and the force exerted by the box on the girl are equal and opposite, okay? So no matter what, if you exert a force on a box, on that object is also going to exert the equal and opposite force on you, okay? So you always got to remember that, and that's always going to trick people, because it's not very. You must think like there's going to be another force that's causing that net force. Yeah. So B is false. And it's pretty easy to identify. Just go like girl on the box, box on the girl. That's equal and opposite, okay? So look at option C. So we know that, so we found the false option. So if you wanted to, we could move on. But let's just go through the other options. So option C, the work done by the girl in pushing the box is converted to heat and or kinetic energy. Okay, so if the box is accelerating, then that's going to be a gain of kinetic energy. And because there is friction, that friction is from the floor rubbing against the box. So you know that when you rub your hands together, they get hot. So that's the friction turning into heat. Okay, so that's true. Option D, the box will speed up if the girl pushes with a horizontal force greater than 100 newtons. Okay, so we can calculate the force of friction on the box because we know the coefficient of friction. So we know that the coefficient of friction is 0.5. We know that the normal force is equal to 200 newtons. And we can calculate the force of friction, which will be in the opposite direction to which the box is moving. So the equation for the force of friction is mu multiplied by n. So the coefficient of friction multiplied by the normal force. So that's going to be 0.5 times 200. So that means we have a friction force of 100 newtons So we have a friction force of 100 newtons acting backwards on this box. And so then if the girl pushes with a force that's greater than 100 newtons, then the net force will be greater than 0. And so then the box will accelerate because there is a net force, right? So option D is true. And option E, so this one's also a bit of a tricky one. If the girl stops pushing, the box will not stop suddenly. It will experience a constant deceleration until it is at rest. So nothing ever stops immediately. It might stop really quickly, and you might think it stops immediately, but there's always going to be even a little fraction of a second where it's going to be decelerating, okay? So E is true because nothing ever just stops immediately or suddenly. There's always going to be some kind of deceleration, and it might just be a fraction of a second so that it's imperceptible to you, but it's happening, okay? So number 4, we have a collision. So here we have a hard metal ball with a mass of 1.5 kilograms, and it collides elastically. So remember what I said in the tutorial before? In an elastic collision, kinetic energy is conserved. So it collides elastically with a hard wooden ball which has a mass of 0.5 kilograms. The collision is head-on. So if one was going, so if the metal ball's going in this direction, the wooden ball is coming in the exact opposite direction. And the balls are in contact for 3 milliseconds. Okay, so we're going to have to convert milliseconds into seconds. Okay, so keep that in mind when we go on to the next part of this question. The collision is relative to the table, the metal ball has a velocity of plus 1.2 meters per second prior to the collision, and the wooden ball is initially stationary. After the collision, the metal ball has a velocity of 0.6 meters per second in the positive direction. What is the velocity of the wooden ball relative to the table after the collision? Okay, so we've got 4 values here, and we know 3 of them. So first of all, it's a elastic collision, which means that kinetic energy is conserved. If kinetic energy is conserved, the relative velocity, so the difference in velocity between the 2 objects is also conserved. That means that you can use this equation. So you can only use the equation that I'm about to write if it's an elastic collision. So V1 minus V2 is equal to V2 minus V1. And this is the velocity before the collision, and this is the velocity after the collision. So the difference in velocity between the two objects is conserved, but they're just going to be in the opposite sign, which is what this equation is saying. Okay, so let's say that V1 is going to be our metal ball and V2 is going to be our wooden ball. So before the collision, the metal ball had a velocity of 1.2 meters per second, right? And the velocity of our wooden ball was 0 meters per second because it was stationary. After the collision, we've been told that the metal ball, so V1, V1 had a velocity of 0.6 meters. Okay, so that might confuse some of you with the minus sign, but so that's 0.6 meters. And we want to know the velocity of the wooden ball, which is V2, right? So then what we're going to do is we're going to add 0.6 to both sides to get rid of this negative 0.6. So 1.2 plus 0.6 is going to be equal to V2, or the velocity of the wooden ball. So that's going to be positive. So V2 is going to then be equal to positive 1.8 meters per second. Okay? So when you have a collision, you can either use momentum, or if it's an elastic collision, you can also use this equation here if you're looking for the velocities. Okay? No, it doesn't. So in this equation, mass doesn't matter. Yeah. Okay, so question 5 is continuing on from the last question. So it's using the information that we got in the last equation. So what is the average force exerted on the metal ball by the wooden ball during the collision? So before the collision, our metal ball was going at a velocity of 1.2 meters per second. After the collision, our metal ball was only going at 0.6 meters per second. So what's happened to the velocity of the metal ball? It's reduced, right? So it must have decelerated. In physics, there's actually no such thing as deceleration. Like, that's not a correct word. You say that it has negative acceleration. Okay, so it's had negative acceleration. I don't mind if you guys use deceleration because everyone knows what you mean. So if it's decelerated or had negative acceleration, it means that there must have been a force acting in the opposite direction to the velocity in order to cause that negative acceleration, right? So this force must have come from the wooden ball. So wooden ball on the metal ball. Okay? So we want to find out the magnitude of this, the force that was exerted by the wooden ball on the metal ball to cause this deceleration. And so if you have a reduction in its velocity, what you also have is a reduction in momentum. So there has been a change in momentum. So the sign here, this sign here, delta, our triangle, means change. So there's been a change in momentum. And we call a change in momentum, there's another word for this, and it's impulse. So the change in momentum or the impulse is equal to the final momentum minus the initial momentum. Okay? So whenever you have a change in something and you want to put it down mathematically, you always do the final value minus the initial value. And that's going to be your delta P or delta whatever. And so there's also another equation for our impulse or our delta P. And that's the change in momentum is equal to our average force multiplied by the time that the force was applied for. Okay? So what we need to do here is we've been given the time in our previous equation, right? So, in the previous question. So we know that the time was 3 milliseconds. So if we converted, so we're trying to remove a prefix, and milli. So milli is times 10 to the negative 3. So we're just going to replace that m with times 10 to the negative 3. 3 times 10 to the negative 3 seconds. Okay? So we know time, and we can calculate the change in momentum by using this equation here. And so we can then figure out what the average force was on that metal ball. Okay, so we're going to calculate our change in momentum. So that's the final momentum. So remember that P is equal to mv, mass times velocity. Our final momentum was, so this metal ball was 1.5 kilograms. So 1.5 times 0.6 minus, so it's got the same mass, 1.5 times its initial velocity, which was 1.2. So that's going to equal, so 0.9 minus 1.8. And if you do that, the change in momentum will be negative 0.9 kg meters per second. Okay, so negative 0.9 kg per second. And that makes sense because remember that force is going to be negative, so it's in the opposite direction to the velocity, which is positive. Okay. So now we've got our delta P. We're just going to rearrange this equation for T. For average force. So force, average, so just you divide both sides by T. So that's going to be delta P over time. And delta P is negative 0.9 over our time, which is 0.003, or you could write 3 times 10 to the negative 3. Same thing. And if you did that, that would be negative 300. Yeah, negative 300 newtons. Okay? All right. So now we have a 20 kg monkey. It's oscillating up and down on the end of a long branch in simple harmonic motion with an amplitude of 0.1 meters and a maximum speed of 0.2 meters per second. And you want to find the Hooke's law spring constant, K for the branch, in Newton meters. You haven't had your simple harmonic motion lectures yet, have you? Okay. So this here, you can treat the branch like a spring. Okay. So the branch is oscillating up and down like a spring. And when you exert force on a spring and you compress it or you send it in one direction, what you're doing is storing potential energy. So remember we talked about potential energy when you're at a height. But you can also store potential energy in a spring, and that potential energy can then be converted into kinetic energy when it comes back. So when it's coming back, it's going to have a velocity, which means it'll have kinetic energy, and then back and forth. So it's going from potential energy to kinetic energy to potential energy and back and forth. If there's no friction, it's just going to oscillate forever. But of course, in real life, there's always going to be air resistance, which is why things don't keep moving forever. So I won't go into the details of it. I'll just show you how to solve this equation. So if you have, let's say this is our branch here when it's straight, and then this is the branch, the maximum curvature of the branch. So then this here would be our amplitude, so just half of it, so just from the midline, we call this the equilibrium position, when it's there's no force being exerted. So from the equilibrium position till the maximum displacement, that's what you call the amplitude, and we give that the symbol A. Okay? So if we write down the variables that we've been given, we know that the mass of the monkey is equal to 20 kilograms. We know that the amplitude, so capital A, is 0.1 meters. And the V max, or the maximum speed, is 0.2 meters per second. And we are looking for K. So K is question mark. So if you had your cheat sheet, and by the time you have your simple harmonic, after your simple harmonic motion lecture, you should have these 3 equations that have K in it. So the first one's going to be T is equal to 2 pi multiplied by the square root of mass over K. Okay, so that's your first equation for spring. And then, so T, capital T is for your time period for one complete oscillation. Your second equation is going to be F, the force, is equal to negative minus Kx. And then your third equation for spring is going to be the energy is equal to half Ka squared. Okay? So the energy stored in a spring is equal to half times the K, the spring constant, multiplied by the amplitude squared. Okay? So here, we want to look for K. So we've got M, A, and V. So we haven't actually got anything that really fits into any of these three equations, right? But we know that the maximum velocity of the monkey is going to be 0.2 meters per second. So at that time, it's going to have kinetic energy. So we can calculate the kinetic energy that the monkey will have. And remember, that's coming from the potential energy of the spring. So we can figure out what what the energy is going to be by calculating the kinetic energy of the monkey. So kinetic energy is equal to half mv squared. So half times 20 times 0.2 squared. That's going to give you 0.4 joules. So that's the kinetic energy of the monkey when it's going at its maximum velocity. And that's going to be equal to the potential energy that is stored in the spring. So now we have E, and we also have the amplitude, and we just want to find what K is. So we're going to rearrange this equation for K. So multiply both sides by 2 to get rid of the half. So that's going to be, so 2E is equal to half, getting rid of the half. So 2E is equal to Ka squared. Divide both sides by A squared. So A squared gets rid of the A squared. So K is equal to 2E over A squared. We'll just substitute the numbers. 2 times our energy, which is 0.4, divided by our amplitude, which is 0.1, and that's squared. And that's going to equal 80. So 80 newtons per meter. So that's going to be the value of K. Okay, so you can see that for some of these questions, you'd have to do maybe 2 or 3 or 4 calculations in order to get your final answer. And you kind of have to be able to put 2 and 2 together to get information that's not told to you directly, but you can calculate or assume from the information that you've been given. So that's why I recommend doing these past papers, because the more you do, the better you'll get at it, and you'll kind of understand what they're asking. Because like when you first start, like it's easy to misinterpret these questions and go in a complete opposite direction of where you should be going. So number 7, we have a spring with a Hooke's law constant of 200 newtons per meter, and it has been compressed by 0.1 meter in a toy gun. When the spring's released, it accelerates a 10-gram bullet out of the gun. What will be the maximum speed of the bullet? Okay, so this one here is kind of like the opposite of what we just did before. So we'll just write down the variables that we've been given. So K is equal to 200 newtons per meter. So we've been told that it's being compressed by 0.1 meters. So if you had a spring, like this, and this is so this here is the equilibrium point where the spring is at naturally, and then you compress it down to this point here. Oops. So it has been compressed by 0.1 meters. So then when it oscillates back and forth, it's going to be oscillating back and forth 0.1 meters up and 0.1 meters down. So remember, our amplitude is just the distance from the equilibrium point to our maximum displacement. So our amplitude is going to be equal to 0.1 meters. Okay? And we know the mass, so they've been kind enough to convert our 10 grams into kilograms, which is 0.01 kilograms. And we want to find out the maximum velocity of the bullet. So the V max equals question mark. Okay, so remember we had our equations before. What we're going to do is we're going to calculate the maximum potential energy of that spring. So E is equal to half Ka squared. That's going to be half times 200 times our amplitude 0.1 squared. So that's going to give you an answer of so can someone calculate that for me? What's the answer? I haven't written it down. So I did another way. What's the answer? Sorry? 1. Cool. So 1 joule. So we have now the maximum kinetic energy of the bullet. So kinetic energy is equal to half mv squared, and we're going to rearrange that for velocity. So v is equal to the square root of 2 times ke over m. So if we substitute our numbers, 2 times 1 over our mass, which is 0.01, we should get an answer of 14.14 meters per second. We've got a 10 kg ladder lying horizontally on the ground, and we've got a 20 kg dog lying exactly on the midpoint of the ladder. And if the dog doesn't move, what's the minimum upward force required to lift one end of the ladder off the ground with the other end resting on the ground? So this is a torque question. It might be slightly hard to recognize as one, but you're going to be applying a force at one end of the ladder, which is going to cause the ladder to go like that, right? Which is rotation, okay? And the fulcrum point will be where the ladder is touching the ground on the other end. So we know that we can assume that the 10 kg ladder is uniform or symmetrical. So that means that the mass or the weight force will be acting in the midpoint of the ladder. So it will be exactly in the middle. So that'll be the weight force of the ladder will be 10 times mass times gravity, which is 10 times 10. So that's 100 newtons downwards. And then we've got our dog, which is just, I can't draw a dog, so I'm just going to draw a box. So that's 20 kilos, and that's going to exert another 200 newtons of force downwards at the midpoint. Okay, so in total we have a downwards force of 300 newtons on this ladder, and what we want to find out is how much force we will have to apply at the end of our ladder in order for us to start to accelerate it. Okay, so the way to approach this is just to find out how much torque is required to keep it level, okay, because that's going to be the minimum force. So torque clockwise is equal to torque counterclockwise. Okay, so that's just F1 D1 is equal to F2 D2. Okay, so let's say this side is, this force here is F1 and this force here is F2. But we have a problem here because we haven't been given the length of the ladder, have we? So how do we know, how can we put D1 in or D2 in? We can't, right? So you're just going to use a little bit of algebra. So from our fulcrum point, we know that we'll call this D1, right? And from the fulcrum point to the end of the ladder, this will be D2. And since this is the midpoint of the ladder, the distance to the end of the ladder must just be twice D1, right? So we can say that D2 is equal to 2 times D1, right? Does everyone get that? Cool. So in our equation, we're just going to put that in now. So force 1 is 300 newtons times D1. And then force 2 is unknown, so we'll just leave that as F2. And that's going to be multiplied by, so D2 is 2 times D1, okay? And so I'll just rewrite that as 300 D1 equals 2 times D1 times F2. Okay, so that's exactly the same thing. It's just F2 times 2 times D1 or 2 times D1 times F2. It doesn't matter what order it's in. So we're going to divide both sides by D1, which will cancel them out. Okay, so that leaves us with 300 is equal to 2 times F2. So divide both sides by 2, you're left with 150 is equal to F2. Okay, so our force here is 150 newtons. Okay? So even if you didn't know how to do this like algebra, you could still have solved this by just using like logic. So you know that force and distance are inversely proportional. Okay, so this is going to be the force that's been applied at the end of the ladder is twice the distance. So you're only going to require half the force in order to produce the same torque, right? So if you see here, 150 is half of 300, right? And that's because the distance is double. Okay. So yeah, even if you didn't know how to do this, you could say, well, the distance is double, so in order to produce the same amount of torque, I only need half the force. Okay. Yeah, I wouldn't bother calculating it. Yeah.
Sorry, I just have a quick question. How many questions do you have in the year?
I think it's 54.
And how many do you have in the like?
Mid-sem, it's 20.
20.
Yeah. So you get 1 hour to do the mid-sem, 20 questions,
Yeah.
and then 3 hours for the final. So it's roughly 3 minutes per question. Yeah. Which is like plenty of time if you don't like spend too long on one question, because most of them you'll be able to do like in under 1 minute, like if you've been like practicing. So number 9, an initially stationary 10 kilogram crate slides from the top of a ramp to the bottom, and the ramp is 10 meters long and 6 meters high at the top. The frictional force exerted by the ramp on the crate is 50 newtons. What is the speed of the crate at the bottom of the ramp? So this is quite similar to that, the man at the top of the slide of the 125 meter tall building that we went through yesterday. So we have the height of this ramp, which is 6 meters, and we have the length of this ramp. So the length here is 10 meters, okay? And we have our box, which is 10 kilograms. And we know that there's a frictional force on the crate of 50 newtons. And that's going to be directed in the opposite direction to the crate's motion, which will be in this direction, right? So the box is at a height of 6 meters, so it's going to have potential energy, right? So potential energy is equal to mass times gravity times height, okay? And as it goes down this ramp, it's losing height, so it's going to lose potential energy, but energy cannot be created or destroyed, so it must be converted, and it's going to be converted into kinetic energy, so it's going to gain velocity. So at the bottom of the ramp, it will have kinetic energy, which is equal to half mv squared. Okay, so yesterday we said that the kinetic energy at the bottom of the ramp will be equal to the potential energy that was at the top of the ramp. And we could use that because there was no friction, but in this question, we do have friction. So we can't just use this simple equation. We have to add something to it. Okay, so we have to calculate the amount of energy that is lost to friction. And the way you do that is to calculate the work of the frictional force multiplied by distance. So work is equal to force times distance. So we know that the frictional force was 50 newtons, and the distance that it was working for was 10 meters. So the work done by friction on the crate is, 500 joules. So that means, so now we have to say the kinetic energy at the bottom of the ramp will be equal to the potential energy that it had minus the work that's been done by friction, or the amount of energy that's been lost to friction. Okay? So if we calculated the potential energy that it had, that'd be 10 times 10 times 6, which is 600 newtons. Okay, so that's 600 minus 500, which leaves us with 100 joules. And so then we know that our kinetic energy is 100, so we're just going to rearrange this for V. So V is equal to the square root of 2ke over m. So v is equal to 2 times 100 over 10, which will be 4.47 meters per second, or it rounds to 4.5, which is option B. Okay, so does everyone understand that? Cool. Well, that's the end of our tutorial tonight. Thanks for coming on a Thursday evening. If anyone has any questions, I'll stick around for a little bit, so feel free to come and talk to me. Cheers.